Hello, good morning, everybody. Just a mic check before we start.
Morning.
All right. Somebody, you can hear me, right?
Good morning.
Good morning. Morning, Dr. ROZMIE. Good morning, everybody who's here today. So, shall we start?
Okay.
Okay. So, first of all, thank you very much for joining us in this webinar. It's the 5th series of Scce Research Knowledge Sharing Webinar, which will be given by one of our own, okay, Dr. ROZMIE RAZIF OTHMAN. Okay, he will present a talk entitled Sequence Covering Array (SCA), the evolution of state transition testing. Okay, Doctor, let me first introduce a bit about Dr. ROZMIE. Dr. ROZMIE received his PhD in software engineering in USM, University of Science Malaysia, in 2012. And his research area includes software testing, optimization, algorithm, and machine learning. He's also a certified professional requirement engineer, or CPRE in short, and also a certified tester advanced level, CTAL-TM. And since 2017, he has been appointed as an associate professor in the School of Computer and Communication, University Malaysia Police. Besides being actively involved in research in locally, he's also been involved in several industries in Malaysia, especially with developing a solution for online systems. So without further ado, let's pass this presentation to Associate Professor Dr. ROZMIE RAZIF to continue his sharing session with us.
Okay, thanks, Jack. Where? Right, okay, sorry, guys, for the interruption. So before we start, I just want to confirm if you can see my presentation slide here. Is it okay? Hello?
Not yet. It's upcoming, I think. Can you press again to present?
Because I want to make it full screen. Can you see it? Can you see my presentation slide?
Not yet. Not for me. Not for me.
Not for you.
Not yet, Doctor. Doctor dah tekan presenting belum?
Oh, okay. Sorry.
Yeah.
Okay. All right. Entire screen. Screen 2. Share. All right. So my presentation slide appear in your site, Jack?
Yes, we can see it now.
Okay.
Okay.
All right. Okay, so Assalamualaikum warahmatullahi wabarakatuh and good morning. Okay, thanks Dr. Professor Dr. Jack for introducing me. All right, so for today's talk, okay, I just want to share with all of you about my my research area. Basically, this is one of my research area. In general, we can say that this is part of software engineering. Okay, software engineering. However, I try to make it a little bit general, so that it can be included as hardware testing as well. So for today's talk, I try to introduce what we call sequence covering array. So basically, this sequence covering array is a new technique, okay, in test design. It's coming from the state transition testing. So we will go through that kind of testing step by step after this. So before, I think all of you, okay, should familiar with what we call state transition diagram. So we can say that state transition diagram is a diagram to describe the behavior of a system, okay, both software and hardware system, to input events. So what the system will react if given to it a certain type of inputs. Okay, so this a diagram that can be understood by technical person and as well as a non-technical person. Also an excellent tools to capture system requirement, okay, and to document internal system design. So this is one from, if you're looking at from developer point of view, okay, we can use these diagrams to record, okay, to capture what is our system requirement, okay, and also the design of our system. And for the tester viewpoint, we can look at this diagram as one of our source to create or to design the test case. So this here is the example of state transition diagram. So this is actually I just created it. Okay, there is no particular system associated with this state transition diagram. This is just a hypothetical, okay, because just want to introduce how a test can be designed from this state transition diagram. So this is basically a system for e-ticket, okay, for e-ticket. So only part of it, So if you have, all right, so we can, when we at the end of buying a ticket online, so usually we will have to select the ticket, whether you want to select the seat. Okay, when we select the seat there, okay, usually when we want to confirm before we make payment, okay, the timer will start. There is a timer that we start, which means that we need to complete our payment within that time period, or otherwise the seat that we have booked will be made available again. Okay, so okay, basically the explanation of this state here I put in another slide. Okay, so in the reserve, okay, in the reserve state, basically what I told you before. Okay, so users should be provided the following information already, okay, to the system. And for this time, okay, at this state, reserve state, the seat will be blocked for this user. Okay, and timer will be start. So user need to finish the payment within the certain time period. So failure to make the payment will result in reservation cancelled by timer. Okay, so if we did not perform the payment before the timer finish, so basically the seat will be unblocked. Okay, and we will go to the cancel by timer state. And if we go further, if we make a payment, then the system will be in the paid state. Okay, if the payment is successful, we are in the paid state. And here the status will be changed to not available. The seat status will be changed from booked to not available, means that the seat already been bought by somebody else. So maybe here user need to print the ticket. For once in confirm state, the username will be inserted. The username will be inserted into the list of passenger. Okay, when the user has print the ticket, okay, it means that the user has confirmed to, has confirmed to go or to take that plane or take the bus. Okay. So at both state, user able to cancel the reservation. Okay. So after paid, user can also cancel the reservation. And also, once you confirm, also user can also cancel the reservation. And finally, at the finish state here, maybe user appear at the given gate, and before entering the aircraft, the user ticket will be scanned. Once the ticket has been scanned, the ticket will be marked as used, so you cannot use the ticket anymore. Okay, ticket information will be used for other purposes such as mile calculation and save in users achieve, save in user archive, and etc. So basically, this is the example I will be used throughout my presentation. Before that, is it clear on the other side? Can I proceed?
Yes, Doctor.
Okay. So this is the summary, the summary for our system just now. Okay, this is the summary for this hypothetical system. So we have several state here. We have reserved state, paid state, and confirmed state, and also the cancel by user state, and finally the finished state. So this is the transition. So from previous state here, so if there is a transition of select ticket, okay, then there will be next state will be the reserve state. And if you are in a reserve state, it's either timer timeout, okay, where we will go to the cancel by timer state, or payment made, it will go to the paid state. Same things goes for paid state. Okay, if user print the ticket, it will go to the confirm. But if user cancel, then it will go to the cancel by user state. And finally, at the confirm state, okay, if user present at the counter, okay, then at the counter, they will scan the ticket and it will go to the finished state. Or if the user cancel the payment, then it will go to the cancel by user state. So how we can the question here now is how we can derive or we can create a test case to test this part of the system. So the first kind of testing here, okay, we can create the test case such that all state, okay, all state here we have a confirm state, cancel by user state, okay, are tested for at least once. Okay, we can create a test case so that all the state will be tested for at least once. So this will lead to 3 test cases. Okay, the first test cases is we start by reserve state, then we make payment, go to pay, we print ticket, go to confirm, and we scan ticket at the counter, then it finish. Okay, this is one test. We try to run this test. If everything work fine, then we can say that this test is the system passed this test. Then we can have a second test. We try to make the reservation. Then we make the payment. After make the payment, we cancel the reservation. So cancel by user, we'll go to the cancel by user state. And finally, we make the reservation and we let the timer time out. So it will cancel by timer. So by looking at these 3 tests, we can say that we have tested all the state. Okay, test number 1, okay, has tested reserve, paid, confirm, and finish state. Test number 2, test reserve, paid, and cancel by user state. And test number 3, test reserve and cancel by timer state. Okay, so all state has been tested, or we can say that all state has been covered by these 3 test cases. However, if we look carefully here, all right, this transition, where if you are in the confirm state, user cancel the transition. Okay, can you see the laser pointer here? Hello?
Yes,
Yes,
Doctor, yes.
Okay. So from confirm state, go to the cancel. If user cancel the reservation when it is in the confirm state, this transition we are not tested. We are not testing this transition. So this is the problem when we are designing our test by just looking at the state. Okay, so instead of focusing in testing the state, it is better to focus on testing the transitions. Okay, rather than focusing on the state, it's better to focus on the transition. Therefore, create test case such that all transitions are tested for at least once. Okay, there is another method. Okay, this is basically the enhancement of previous method, where now we are looking on testing the transition. So if you design the test case so that all the transition in the previous system is tested, we can have 4 test cases, which are this one. Okay, these 4 here. Select ticket or start timer, payment made, print ticket, scan ticket, select ticket, start timer, payment made, print ticket, cancel by user, and these 3, another 2 here. Okay, So if you look at the state transition diagram, the first test, okay, we select type ticket, start timer, payment made, print ticket, and scan ticket at the counter. This will be the second test, okay, select ticket timer, select ticket, start timer, payment made, print ticket, and cancel by user. And this is the third test, okay, select ticket, start timer, payment made, and cancel by user. And finally, the select ticket, start timer, then cancel by timer. Okay, all right. So this is, if you see here, you can say that, okay, this is a very good test design technique. This is a very good test design technique since we have covered all states and we have covered all transitions. Okay, at the same time, we cover all state and we cover all transition. The only problem, if you are looking at this kind of test design technique, is that if one of tests fail, okay, for example, let's say test number 1 here, the green test here is failed. When you run this test at the system, the test failed. We cannot pinpoint in which transaction or in which transition is actually the where the problem caused. Okay, it's either at this transition or maybe at the last transition. We don't know. Okay, it cannot exactly pinpoint where the error is actually located. So there is another technique of designing test case from state transition diagram to cater this problem. So the same thing, we still focus on the transition. Okay, we still focus on the transition, but we don't really care about the overall flow of the process. So what does it mean? Is that we just testing each transition for one test cases. For one test, we just test one transition. So initial state will be made as precondition. So for example, I want to test this select timer or select ticket or start timer. I just test this transition only for my first test. Okay, so previous state, okay, this will be the previous state coming from previous state. And we run this one, okay, we select ticket or start timer. Then we look, if the next state is reserved state, then we say that this system passed test case number 1. Okay, the same thing goes for the test number 2. Okay, test number 2, we have to make our system at the reserved state first. Then we try or we test the transition timer timeout. Okay, we look at the next state, what will happen to the system. If the system goes to the cancel by timer state, then we say that the system passed test case number 2. And the same thing goes for the test case number 3. Okay, so for each transition, we have one test. Okay, we have 4, 5 to test transition, cancel by user, and print ticket. And 6, 7, and okay, in total we have 7 test cases to test each individual transition. So for this, what we call one switch testing here, okay, one switch testing means that we test one transition at a time. Okay, so we can say that all transitions are tested. Okay, all transitions are tested, and then number of test case is greater than previous technique, of course, because now we just test one transition at a time. Okay, so surely the number of test cases will be increased. But each test case corresponds to only one transition, which means that it's easy to trace back the error when failure occurs. We know that which transition is causing the error. But the question now is it enough to test one transaction or one transition at a time? Okay, only one transition at a time. How about if the failure occurs due to the successive occurrence of more than one transition? Or we can say that the interaction of transition will cause the error. I can give you an example. For example, select ticket and timer timeout. If these two happen at the success, what we call that, in sequence, okay. If timer select ticket and timer timeout happen, then the failure will occur. So this kind of bugs, okay, cannot be detected by just using one switch testing only. So it means that we need to go beyond one switch testing. Maybe we have to go to the two switch testing here. Okay, we have to go for more than one transition, testing one transition at a time. So there is a suggestion to have what we call N switch testing. So more generalization of state transition testing, where N will be represented by the number of successive occurrence of transition in each test cases. So N value will be decided by test designer, okay, based on requirement or their experience or maybe the risk analysis. Okay, so what is the two switch testing? Two switch testing where I specify N here as 2. So two switch testing means that we will have two transition tested at a time. Okay, two successive transition tested one at a time. So for example, here we're starting from initial state. We test select ticket and start timer transition, and also payment made. Okay, and then the last state would be paid. Okay, and then the test case number 2, we test select ticket or start timer, then timer timeout. Okay, we see where it will go to the cancel by timer. So these two transition at a time test is what we call two switch testing. So by designing the test using two switch testing for the same system, I think we will have around 6. Okay, this is around 6 test case. Around 6 test case. So it is a little bit less compared to the one switch testing. But in general, we cannot conclude something like that. And sometimes we have more state than the two switch testing. Sometimes will be more than one switch testing. So in general, we can say that N switch testing it is a good test design technique for designing test cases from state transition diagram. So we give the flexibility to test designer to choose the N value, okay, whether we want to have one switch testing, two switch testing, or three switch testing. It depends on the test designer. So able to produce the test cases that cover all possible transition. All possible transition. Okay, test all the possible N interaction of transition. Okay, and of course at the same time, all right, all state will be covered by the test as well. So depending on the system risk, okay, the test cases for some or all of the invalid transition are also required in order to make sure that the system has not implemented any invalid transition. Okay, in software testing area, we call this one as negative testing. It means that we test something is not designed to the system. Okay, for example, that I give you the example here. So let's say we have a select ticket and start timer. Okay, we go to the reserve state, and once we have made the payment, okay, and it will go to the paid state. Okay, so if you are designing this system, okay, means that if you are coding this system, we should stop the timer once the payment has been made. Okay, once the payment has been made, the timer should stop. Okay, so once in the paid state, we cannot go to the cancel by timer state. So here, okay, in case of timer failure, system should not be allowed to do this transition because the customer has already made the payment. Okay, even if the timer is not stopped here, okay, it's not stopping, the timer is still continue to count the time. Okay, even if the timer is time out, then we shouldn't allow this kind of transition. Okay, this is what we call invalid transition. So as a tester, okay, we need to test this kind of possibility as well. Okay, so previously when we test payment made here, we assume that from reserved state, it should go to the paid state. Now, we want to make sure that from paid state, we didn't go to the cancel by timer state. This is what we call negative testing. So negative testing, we are not talking about negative testing in the previous test design technique. Okay, so if the test case is derived from the available transition, surely invalid transition won't be tested. So now let's say we forget about the transition. Now we go back to the state testing. We focus on the state. So derive the test case based on the transition between n states. Okay, we are focusing now on state back. This kind of testing may lead to beyond combinatorial explosion problem. This is later I will demonstrate what we call by the beyond combinatorial explosion problem. So let's revisit the same system again. Okay, but now in order to facilitate the presentation, I label our reserved state as A, paid state as B, confirmed by C, state as D, and so on. Cancel by timer E, cancel by user F. So this is the, just to simplify my presentation. So for state A here, okay, for reserved state, or we can call it as state A, we may have 5 tests. Okay, A go to B, A go to C, which is invalid testing for A go to C. Sorry, A go to C is valid. Okay, let's say we can refer to the slide transition, state transition just now. Okay, we can have A to D testing. Okay, from reserve go to the finish. Okay, this is an invalid testing. From reserve go to cancel by time. Okay, and from reserve go to the cancel by user F. Right, and same thing go for the second state B. Okay? B go to A, B go to C, B go to D, B go to E, and B go to F, and so on. Okay, and actually we will have around 30 test cases. Okay, we test A go to B, can A go to C, or and so on. So a total of 30 test cases are derived from 2-state testing. So now I'm switching from 2-switch testing to 2-state testing. This to represent that now we are focusing on state. We are focusing on state. 1 transition, but 2 state. Okay, note that for 2-state testing, we only consider 1 transition, either valid or invalid. We consider both. Again, failure might caused by the interaction between 2 or more transition. Okay, again, the same things we have discussed before. We can have a successive transition that can cause bugs. So then we can have a more generalized version of n-state testing. We can have 3-state testing. Okay, we can have A go to B, go to C, A go to B, go to D, and so on. All right. So if you're looking at this, okay, you can say that if you are go for the permutation here, you can see that this is a permutation. We can have around 133 test cases to be tested, okay, for this portion of system, e-ticketing system. Okay, since this is quite a lot of tests for a very small system. So given a system with V state, okay, so and the N state testing will be result in F number of test cases. Okay, where F is actually V factorial over V minus N factorial. This is basically the permutation calculation. So the highest number of test cases in V state testing, we can say that when N is equal to V, which is F is equal to V factorial. So for ticket reservation example, we have V state testing will result in 720 test cases since we have 7 state, right? We have 7 state, so 7 factorial. Sorry, we have 6 state, we have 6 factorial, which is 722 test cases. So it should be noted that the number will increase exponentially with the increase of V. So if the system has more state, okay, then the number of test cases will be increased exponentially. So this is why I say that this end state testing can result in the beyond combinatorial explosion problem, because when we're talking about combinatorial exponential problem, we are talking about combination. But now we are not focusing on combination. We are going for permutation. Okay, if someone from the mathematics field, they should know that combination and permutation will result in more numbers compared to combination, because in combination, A to B is considered and B to A is considered the same things. But for permutation, AB and BA is considered as two different things. So that's why for permutation, we'll be causing a lot more test cases. So here's come what we call sequence covering array. Basically, the idea of sequence covering array is introduced by Colburn in 2012. Okay, this part is a little bit more, mathematics. Okay, Colburn gave the definition of sequence covering array, okay, as an array of order V and strength T is given by this set, okay, where pi I is a permutation of 0 until V minus 1, and every T sub-permutation of 0 until V minus 1 is covered by at least one of the permutation in this set, covering array set. So this array here can also be represented using covering array notation, SCA, okay, and semicolon T comma V. So this is mathematical modeling for this covering array. So what does this actually mean? Okay, a T sub-permutation of 0 until V minus 1 is actually a T tuple from x1 until xt, with xi is a subset of 0 until V minus 1 for I between 1 and T inclusive. Okay, a permutation of pi from 0 to V minus 1 is said to cover the T sub-permutation of xi until xt if the location of xi in pi is less than xj in pi whenever I is less than j. So we look at this example here. If I say that we have V equal to 5 and T is equal to 3, so our T sub-permutation, for example, let's say 403 here, 403 is a 3 sub-permutation that is covered by the permutation 42031. Why we say that this 403 is covered by permutation 42031? Because in this 3 sub-permutation here, 4 occurs before 0 and before 3, and 0 is occurs before 3. And we look at this permutation here, 4 is actually occurs before 0 and 3, and 0 is occurs before 3. So that's why we say that this sub-permutation is covered by this permutation using this definition. Okay, it says that xi here, xi in pi, in the permutation here, should be less than the location of xj in pi here. So for example, if I take xi here as 4, okay, 4 in this permutation happen at index 0. And 0 here in pi, in this permutation here, occurs at index number 2. So of course 0 is less than 2. Okay, so that's why we can test for any element here. Okay, and this statement here will be true. Okay, if this statement here is true, then we can say that this 3 sub-permutation is covered by this permutation. Okay, for example, this 403 sub-permutation here is covered by this 42031 permutation here. So how we can apply this one in our covering array in testing our end state testing here. Okay. So let V representing the number of state in the system and T representing the number of successive transition that we want to test. Okay. Then the T subpermutation in covering array will be the T state testing test cases. Okay. And the covering array, okay, the resulting covering array can represent a complete test case for the permutation of the events. At the same time, the sequence covering array, okay, the sequence covering array is a set of test cases, or we can say that test suite that cover all the T-state testing test cases for at least once. Okay, so let's look back at the system that I have shown to you just now. Okay, we have 6 state. Okay, 6 state for this system, A until F. And then let's say I want to design a test cases for 3 state testing. Okay, 3 state testing means that 3 state per test cases. Okay, and this SCA 1036 here, I'm taking from these references. Okay, okay, this is basically a project done by National Institute of Standard, if I'm talking the NIST, US. They have produced 10 test cases that can cover all the 3 state testing here. So let's check its correctness. So let's say we verify this this covering array here. So this is the covering array, right? This is the test cases I'm taking from previous slide. So for example, A, B, C, A go to B, go to C. We can see here, this one is covered by the test case number 1. Okay, A go to B, go to C, means that A happened first, then B, then C. Same things for A, B, D, okay, still covered by test case number 1. So because A happened first, then after A, then B, then after B is, okay, D. So D basically happened after B happened, okay, after B has occurred. Say, and then the same thing go for ABE, ABF. Okay, this one all covered by test case number 1. ACB and ACD here we can say we can see it at test case number 7, ACD and also ACB. All right. ACE at test case number 5. Okay, A go after A, C, after C is E, and so on. So if we look at all the 3 state testing test cases, all the state all the what we call the transition here is actually happen in this covering array. Okay, sequence covering array of 10 semicolon 3, 6. Right, we can look at all the state transition, okay, state 3 states testing, right? So everything basically we can pinpoint, or we can trace back into this what we call this covering array, this covering array, sequence covering array. And we can say that we have 100% coverage of 3 state testing using this covering sequence covering array of 10 semicolon 3, 6. So this is how actually we can implement, okay, the sequence covering array in testing the system, okay, based on the state transition. All right. So challenges in designing tools for generating SCA. So the first challenge will be the algorithm. All right, the algorithm to come out with the most optimum covering array will be challenging. Okay, the problem is fall under NP-hard computational problem. So no single algorithm able to produce the smallest SCA in terms of covering all the array size. Yeah, in terms of covering array size. And okay, because of course we want to have less test case, okay, in our testing, because later on in test execution we don't need to have too many tests to be tested. And another thing would be a challenge in this area is the data structure. Okay, because we need to store the T subpermutation. Okay, because in generating the sequence covering array, we need to make sure that the sequence covering array is actually covering all the T subpermutation. So in creating the program or the algorithm, surely we need to generate the T subpermutation first, and then we go to the process of creating the sequence covering array. All right. Then we have to verify whether all the T subpermutation has been covered by sequence covering array or not. Otherwise, that covering array won't be called as a covering array, because if it didn't cover all the T subpermutation. So if you are in this field, basically the data structure is very important in order to make sure that our algorithm can produce what we call it's not a perfect, but it's a correct covering array. And another open problem for this system, okay, this is not only previous I explained about the challenges in designing the algorithm or designing a tools to generate the covering array. In testing, there will be more. There will be some open problem that we need to consider in using this sequence covering array. The first problem is what we call constraints. Some transitions are impossible to be implemented. So how we are going to exclude this transition from SCA? For example, maybe based on our previous example, we cannot jump from start timer to the finish. Okay, for example, completed. That transition is impossible. But if you look at our solution here, there will be A going to E. For example, let's say I show you. All right. So here we can say that we have tested A go to B and directly go to E. All right. Or we can say that A go to B or go to F. Maybe B go to F here is impossible. Okay, B go to F here is impossible. It's impossible to be implemented in the real world testing. So how to exclude this transition in generating the covering array? This would be one of the open problem that need to be considered as a possible research area. And another thing is about repetition. Okay, repetition. It is common to have a transition that loop to its current state. For example, like this state transition, where this transition is back at this state. So up until now, we didn't discuss about this and how to cater the repetition transition. And basically, there's still no research in this area yet. Okay, in this area yet. It can be a potential area for research, okay, on how to cater this repetition. And I think that's all from me. All right, maybe we can open this session, floor for Q&A session. Right. So Dr. Jack, I pass the mic to you.
It's okay. Maybe Dr. Jay can't hear at the moment. Okay. We open to the floor for any question and answer. Any questions?
Tak ada soalan kot.
Okay. Dekat FB pun tak ada question setakat ni. So okay. Okay. If there is no other question, I would like to ask for if you could fill up the feedback form. Okay, I've shared the link at the chat room. Okay, that one is for the feedback. Okay, last but not least, can you please turn on your camera for the group photo session? Okay, ready? Okay. So for that, okay, thank you very much, Dr. Associate Professor Dr. ROZMIE RAZIF OTHMAN, for the nice presentation. Okay, if you do have any question, maybe you can email to him. Okay, and thank you very much for all the audience. Okay, see you again for next webinar session. Okay, thank you.
Okay, thank you all.
Don't forget to fill up the feedback form, yeah?